Okay, so slope fields you can do in higher order, but for us, we're going to be doing first order DEs. So we'll have some first order DE. And we're going to have it in standard form, some y prime equals some function of x and y. Then we're just going to plot out in the xy plane. We're going to make up a whole bunch of points, x and y, and then we're going to plot the slope at that point because that's what y prime is. Y prime is the slope. So we're going to plot f prime at that point. So we're going to grab a point xy, say our point is the point 2,5, and we plug in 2 for x, 5 for y over here, and we get a slope of 7. Then we're going to plot a unit vector with a slope of 7 at that point. And maybe we plug in the point, so maybe we had this. Maybe we plug in the point 2, 6. And we plug that in here, and maybe we get -3. So then at the point 2, 6, we're going to graph a unit vector of slope -3. And we're going to do that all over the plane. We're going to plot a whole bunch of these, and that's called a slope field. Okay, so let's do like a quick example. We're not going to plot a whole bunch of points by hand, and then I'll show you some software that will do it for us. So say, for example, we had 2x minus y. So I'm literally just making up a whole bunch of points here. So maybe we could plug in 0, 0, 0, 1, 1, 0, -1, 2. I think that would be enough. Okay, so at 0, 0, y prime would be 2 times 0. I'm literally going to write it all out, even though it's obvious. Y prime would be 0. So at the point 0, 0, I'm going to graph a unit vector of slope 0. What was the next one? It shows 0, 1. So 0 for all the x's, 1 for all the y's. Y prime will be 2 times 0 minus 1. I think that's -1. So at the point 0, 1, I'm going to plot a unit vector that has slope -1. 1, 0. So 2 times 1 minus 0 will be 2. Oh, I plotted that in the wrong spot, didn't I? 0, 1 would be here. Sorry. 1, 0 have a slope of 2. So I'm just kind of estimating that. I'm trying to keep these all the same length. -1, 2. So 2 times -1 minus 2. So that'd be what? -2 minus 2. I think that's -4. So at the point -1, 2, I would have a slope of -4. So he would be a lot more down. And we're always thinking going left to right. So I'm never going to draw my vectors going backwards. We're always going to assume that our x's are increasing. So my, just like we always do with slope. So all my vectors are going to point over in this region over here. They're going to point left to right, either up if they're positive or down if they're negative. And we could continue this and plot thousands of points and fill this thing up with little vectors. And then it would look like little current vectors. So I've already done that. So I just literally Googled slope field plotter or slope field generator. And there are a bunch of them out there that are free. These work perfectly fine. This is the one I like the best, and that's what I'm using. And I can control like what range of X's and Y's I want to see. I can control how dense they are. So I can plot a bunch more or a bunch less. And I said unit vector, and it doesn't, that's not what's important. What's important is that all the vectors have the same size. They don't necessarily have to have length 1. See, changing the length doesn't change my vector field. So I can plot more of them, I can plot less. Then we can visualize what solution curves will look like by just imagining if I put a little boat here, all of these vectors here show us which way the current is flowing. Imagine that this is a river flowing and we're literally looking at the currents. If I were to drop a little boat right here at this point, it would flow down, it would follow these vectors and then flow up. And if I move that starting point around, I would follow a different current. So we can use a slope field to draw graphs of solution curves. And depending on our starting point, we're going to follow a different curve. Remember, the solution to a DE is an infinite number of solution curves depending on your initial value. So really, all I'm doing here is changing my initial value, changing my C. So here are all my different C's. I get different curves. Okay, so for fun, let's plot some different slope fields. So anything that is of the form y prime equals some function of x and y, I can plot here. I can plot, I don't know, maybe e to the x plus cosine of y. And that might look like that. Notice how it's got a little bit of waviness in it from that cosine. I could do, I'll say negative x over y. Now, the problem with these slope field generators is when they try to plot these curves, they always assume, like I said, that you're going from left to right. So the way it plots this green curve we're looking at here is it uses something called Euler's method that we're going to learn next. And Euler's method assumes if you're on a curve, you're going to keep increasing your x value. This solution curve is not correct. That green curve is wrong. And the problem is once we get to this point right here, the real solution curve is a circle and it comes back on itself. I mean, this is a classic DE. We could easily solve that. Y prime is negative x over y. I think that may have been on the first test. The solution is x squared plus y squared equals a constant. It's our solution, our curves, our circles. So this field plotter will not properly come back on itself like it should. Once it gets right there, my x's start decreasing and it doesn't know what to do with that. So it jumps ahead to the next curve. And then once it gets down here, it jumps ahead. It's all messed up. So this is not a foolproof way to get curves, but at least part of our solution curve will show. This part right here is correct. Okay, so how are we drawing this green curve? Using something called Euler's method. So for the second project, you're going to use Euler's method to draw some solution curves. You're going to be doing this on the test, in the group assignments, on the project. And like, this is one of my pet peeves, is when people mispronounce this guy's name. He's a very famous mathematician, a whole lot of number theory, calculus, can be attributed to Euler. Please don't call him Euler. Euler. It's pronounced oil. Okay, remember from Calc 1, linearization. When you were finding the equation of a tangent line, you had some curve, and you want to find the equation of the tangent line right there, y equals mx plus b. The way you did that was by approximating, by saying f of x near some x naught is approximately equal to f at x naught plus the derivative at x naught times some change in x. That's literally just, if I move this point over here, if I write this, f of x minus f of x naught and then say I divide this over approximately change in y over change in x. That's just the formula for slope. That's literally all that is. Because that's what the derivatives gives us. The derivative gives us the slope at a particular point. This is saying if you're near that point, your slope should be close to what it was at that point. So the function values, if I'm on a curve and I know one point on my curve, what I'm going to do is use the slope at that point to find another point. So I'm going to say, oh, well, the slope is in this direction. I'm going to then move over and up that amount and say that that function value is quite near the point on the line that's tangent here. Here's my x naught. And then we continue that process. We move on. It's an iterative process. Now I use this as my new seed, my new starting point. I find the slope at that point, go over and up, and get a new point. So we're approximating our curve with a bunch of little line segments. In other words, in our slope field here, I'm starting at this point and I'm looking at that little slope right there. And I'm saying, okay, I'm going to go down to get to my next point. Now that I'm here, what's my slope look like? Oh, it kind of goes this way. So I go down a little bit. Oh, now I'm going at this angle and so forth. And you just follow, it's literally just following these little slopes. Now, the key to how accurate this picture will be is that step size right there. See, if I change this step size, my graph will not be nearly as accurate. See how clunky it is now? That step size is here. That change in x, that's called our step size. So when we're using Euler's method, we start with what's called a seed. That's our initial point. That's when I'm plotting these, that's at that point A right there. Say I wanted to start at the point -1, 1. Or actually, let's see, what point did I start at? -1, 0. So I'm going to start at that point. So for example, say I use -1, 0. Then I'm going to approximate another point on the graph by saying the next point, f at x number 1, should be approximately my initial point, my initial y value, plus the derivative at that initial y value times my change in x. So that's my delta x, or my step size. And this is my starting point, my seed. Then once I get this, this will give me some approximate value for f of x1. I use that to build the next one. F of x2 should be approximately the last y value plus the derivative at the last y value times my change in x. Change in x, we should just keep constant, so I don't have to keep writing that. That should just be the same for each one. And we just keep going. Approximately f at x2 plus the derivative at that last point times that step size. And we could go on as long as we want. And this will build us a bunch of points that we can then plot together. Okay, so let's do a few of these by hand. And then I'll show you how to do Excel, plug all this into Excel, and it'll just do it for you. So this is the guy I'm going to be plotting out. And I'm going to be starting at, what did I say, -1, 0? Yeah. And I'm going to use a step size of 0.1. If we go smaller, we'll get a more accurate graph. If we go bigger, we get a less accurate graph. Okay, so I'm going to plot or make an XY table here. And here, let's say step 0, 1, 2, and so forth. And we'll actually by hand calculate a few of these. We don't really need this column, but I'm going to put it in there anyways. This one I'm stuck with. That's my starting point, -1, 0. So I'm going up by 0.1. I can already fill in all my x values. I'm just going to keep increasing by 0.1. So -0.9, -0.8. My third step will be -0.7. I'm just increasing my x's, and my goal really is just to find all my y's. So at x equals -0.9. So this is step 1. F, the y value at -0.9 should be approximately equal to the last y value. So that's step 0 plus the derivative at the last y value times my step size. I know that last y value was 0. Now I got to find the derivative at that last y value. So I'm going to do what we were just doing. I'm going to plug -1 in here. So here's a little side work. F prime at -1 comma 0, because I'm plugging in this last point, would be 2 times -1 minus 0. Was that -2? You guys correct me if you see me make any mistakes here. I'm doing all this by hand. So -2 times my step size, 0.1. So I think that's -0.2. Okay, then we just repeat. Now this is my new starting point. So at step 2, so I'm at x equals -0.8. The y value there will be approximately the last y value, f of negative 0.9 plus the derivative at the last y value, at the last x value, the last point, times delta x. My last y value was negative 0.2. Now I got to plug this previous point into the derivative, into the dE itself. So f prime at negative 0.9 comma negative 0.2 would be 2 times negative 0.9 minus 0.2. We get whatever we get. I think you're seeing the process now. Take that times our 0.1, our step size, our delta x, add that to 0.2, we get that y value that goes there. And then we just continue. We just do this over and over again. It's pretty easy to program Excel to do this for us. Okay, so I've already got it here. I've already done it. Let me show you how I typed it, and then I'll literally just start over and do the whole process again. Look, I can even tell Excel to draw one of my solution curves. And then I can easily change my seeds, change my starting point, and then scroll down. And that, yeah, that did it. That changed everything, including my graph. It started at 3. So I could easily look at solution curves, approximate solution curves, pretty easily. But we were doing, what were we doing? -1, 0. So what we want to do here, we put our seed point right here, -1, 0. Then I want to put in all my x values. So I did, this point is going to be the previous point plus 0.1. That's my step size. I decided I wanted to go by 0.1. Then I drug that down because I wanted to go all the way up to x equals 2. I could have kept dragging, go all the way up to x equals 10 if I wanted, or whatever. Now I need to find each y value. So this next y value will be the previous y value plus, here's my derivative at the previous point. Remember, my dE was y prime equals twice x minus y. So twice the previous x minus y times my delta x. I hit enter, and then I can grab this little corner and drag this down. That fills in all my y values.
We can only see the whiteboard right now.
Oh my, so I went through all that and nobody said it.
Sorry, I thought you were dictating and they were going to show us like afterwards.
So you didn't see any of that?
Not the inputs for Excel, no.
Oh, okay. I have to redo that whole thing. Sorry about that, guys. Okay, so I said it all so perfectly too.
Oh my God.
Okay, so I've got a list of points here that I can tell Excel to graph. These are points on this solution curve, or at least approximate points. Remember, Euler's method is not perfect, but if you take your step size to be small, you'll get a really good approximation. As long as your function, your solution curves are functions, as long as they don't curve back on themselves, and as long as they pass the vertical line test, Euler's method is fantastic. If you have any sharp corners in your solution curves, like if your solution curve goes up and like an absolute value suddenly juts down, Euler might mess up that junction there. Any place where the derivative has issues, if the derivative is undefined, Euler's method is going to have issues. Otherwise, it's a great approximation tool. Okay, so I've put here my seed, -1, 0. Then I wanted to just auto fill in all my x values. So I went to the next cell and said, take the previous cell and add my step size to it, 0.1. I could have chosen any step size I wanted here. I chose 0.1. Then grab my little corner and drag down, and that will generate all these X values. Now I need to find all my Y values. So I take this cell here and say, I want this Y value to be the previous Y value plus the derivative at the previous point times my step size. So my derivative was 2x minus y, twice the previous x minus the previous y times delta x, hit enter, and then I drag down. That will generate all my y's. And then I can go to insert, chart. I can do scatter or line, either one, and I can generate this graph. Okay, so let's do a brand new one so that you can watch it from the beginning. Okay, you guys, somebody make up a DE. Something relatively simple. Y prime equals a function of X and Y. Anybody yell something out.
Y prime equals 3x plus 4. I'm sorry.
3x plus Y.
3x plus
How's that?
y. I just got
Okay.
a y in there.
Yeah, we don't have to have a Y in there, but let's put a Y in there. And let's pick a starting point, our seed. Let's say our seed is 2, 3. So I'm going to put my seed in. I like to, Excel has changed over the years. Back in the day, when you were typing in a number that you wanted it to see as a numerical value, you had to hit equals. I had to hit equals 2 equals 3. I don't think that's necessary anymore, but I'm still in the habit of doing it. Here, I definitely have to hit equal. So I'm going to use a step size of, again, 0.1. So I'm going to hit equals. I'm just going to click on the previous cell. I want the last value plus 0.1, enter. And let's go all the way up to 5. There. We'll go to 7 because that's what I drug to. Okay, now I want this Y value to equal the previous Y value plus my derivative. I'm going to need parentheses here. My derivative was 3x plus y. So 3 times the previous x. So times previous x, not the current x, plus y, the previous y, close my parentheses, times my delta x, which we used 0.1. Hit enter, and then grab this little corner and drag it down. So this guy grows pretty quickly. The solution is probably an exponential curve of some sort. It's a first order linear DE. I know we could solve it, but we want to get practice solving numerically with some easy ones before we get into ones that we couldn't solve. I mean, in the real world, we would just solve the DE, right? It's first order linear. We get an integrating factor. It's not that hard. Okay, now I like to highlight both of these columns. Go to insert, chart. I think we could do it with a line, but I prefer the scatter. And look, we get some kind of exponential curve. And then what's really nice is I can easily change my seed here, and the graph, everything will change. What if I pick negative x values? Oh, we get some negative exponential. If I pick a negative y value, Okay, questions on the process?
It's fairly straightforward.
We do have a group assignment coming up on this. So I've told you what seed to use. I've given you a starting point. I've even started filling in the table. I want you to do these by hand. I mean, of course, you're going to get your calculator out, but I want you to actually, even you got space here, write up all those little steps like I was for how you found each one of these. Then use Excel to do a lot more. Go 500 steps. So you got to keep in mind when I say 500 steps, this was step 0 right here on line 2. So I would want to go all the way to 502 to make that 500 steps. So you want to drag all the way down to line 502. But we're going by a smaller amount. Our delta x here is 0.01. So I think, let's see, you should only be going then from 0 to 5. My arithmetic is correct. Yeah, that'll get you from 0 to 5. So do that in Excel, create the scatter plot, and then just copy and paste this over into your document. So my recommendation is do this in a Word doc. Is my file a Word doc? No, it's a PDF. Okay, then my suggestion is don't try to do it on my sheet. Do this whole thing in a Word doc. Create your own table, upload it all, and you can upload it as a Word doc. Nope, I do say save it as a PDF, so you do want to save it as a PDF. Okay, so this is what you'll be turning in. Please don't turn in all 500 rows here to me. I don't need to see this. I want to see just the graph. Now, let's be honest here. Anytime you're turning in a graph, you should have a well-labeled graph. So you want to go in and make sure you label your axes. And in different versions of Excel, that's different. So you may have to go to add over here, add titles, labels. Does that make sense? Don't add a trend line because our answer definitely won't be linear. But add on labels here and make sure you say X and Y.